Okay, so welcome to Math 355 Abstract Algebra. This is lecture 15. And so what I want to do today is finish off the parts of chapter 6 that we're going to do, which is our next exploration of groups, orbit stabilizers, and the first of the Sylow theorems. So the idea is to try to understand what are the possible structures of groups. And so to do this, we're going to come up with some really nice ways of attacking groups and extracting information from them. Okay. The first thing is we're going to define a new process, a group acting on a set. And so depending on what choice you make, there's going to be many different ways to have a group act on a set. And there'll be many different choices of what would be a good set for a group to act on. So we're going to define, or we're only going to consider groups acting on sets with the following two properties. So first of all, if I give you some element little x and x, and I give you some element g and g, I've got to associate an element in the space x from this map. So really, we're creating a map f sub g, which takes x to x, and we'll look at little f sub g of x. And we want this mapping, this association to group elements to maps, to have the following two properties. The first is the identity. If I take my element to be the identity element, I want it to leave every x alone. And that's where the first property comes from. Ex is just x. And the second is the associativity. That if I look at G1, G2 acting on x, that's the same as first act on by G2, and then act on by G1. So we could say we want f of G1 of f of G2 of x to be the same as the map associated to G1, G2 of x. And then again, it's not clear when are we going to be able to find group actions? When are we going to be able to find a group, a set, and an operation such that this will be true? And so what I want to do is I want to start off with an interesting non-trivial one. So let's let G be GL2 of R. So this is the set of all 2x2 matrices. A, B, C, D are real, and the determinant is non-zero. So these are invertible matrices, and it is a group under matrix multiplication. Let's let X be the set of all Z equal X plus I, Y. So these are all complex numbers, such that Y is greater than 0. And we often write this as H for the upper half plane. This is an extremely important example in number theory. And so we're going to define a way to have groups act on complex numbers. Where have you seen matrices acting on things? What have you seen matrices act on? Vectors. And this idea of AB acting on a vector B should be B acts on V, and then have A act on that. This is some kind of generalization of that. And we're going to define things as follows. So A, B, C, D acting on Z is going to be AZ plus B over CZ plus D. And that's going to give me a complex number. As an exercise, you need to show that this is also going to have real part greater than 0, that this is in the upper half plane. So I'll leave that calculation to you. Whenever you see a fraction, what is your first fear? What scares you? Dividing by 0. And since Z has positive imaginary part, there's no danger that I'm going to divide by 0. Now we need to check and see, is this well defined? Well, if I take the identity, 1, 0, 0, 1 acting on Z is going to be 1Z plus 0 over 0Z plus 1. That is Z, yes. And I'll leave it to you to check the other property of associativity. Matrix multiplication will be very useful. And so you can check and you can see that this is going to be a group action on the set of numbers in the upper half plane, on these complex numbers. Now, the next thing is we're going to define two new sets. And unfortunately, if you have bad eyesight, the notation is going to look like the same. So the first is the orbit. So what is the orbit? Well, I take some x, and then I just apply every element in G one after the other after the other. And I look at all the different outputs, and I call that the orbit. The next thing is I could say, well, if I take an x, which elements of G leave x alone, leave x fixed? And that's going to be called the stabilizer. So they're both Gx. One of them is G subscript x, that's the stabilizer. The other is Gx, where x is normal size. When you're doing things in tech, it's not so bad to do this. When you're writing things by hand, it can be a real pain. So I will try to put little notes, stabilizer, orbit. If you are writing things by hand, try to be very clear, is it a stabilizer or is it an orbit? And so the question might be, if I give you a group action in a set, can you find the stabilizer? So if we take our example from before, where G was, GL2 of R, and X was the upper half plane, what is the stabilizer of some element Z? So I want AZ plus B over CZ plus D equals Z. How would I find that? So how would I find which matrices give me Z back? I'm sorry? Okay, so how would I solve this? This is an equation, Z is fixed, and I have 4 unknowns. Okay, so we get AZ plus B equals CZ squared plus DZ. Z is fixed. And Z is C. So, okay, so can you give me something that's going to be in the stabilizer? Okay, so we know the identity is in the stabilizer. So 1001 is clearly always going to be in the stabilizer of Z. Can you give me something else that's in the stabilizer? Something closely related to the identity matrix. Good, so if I multiply by -1, in fact, more generally, if I multiply this by anything. So if I give you A00A acting on Z, that's AZ plus 0 over 0Z plus A, that's just Z. So all diagonal matrices are in the stabilizer. Is there anything else? And so I'll leave that as an exercise for you. I want to just talk a little bit about how you might attack this. I claim there's 2 cases. Case 1, A equals 0. Case 2, A does not equal 0. So if A equals 0, then our matrix is going to be the form 0, B, C, and D. If A does not equal 0, it's of the form A, B, C, D. And when it acts on Z, we get AZ plus B over CZ plus D. But because A is not 0, I can pull it out. And I can pull it out from the denominator, and I'll get C over A, Z plus D over A. And the numerator will be Z plus B over A. What can I do to the 2 A's? I can cancel. So this is the same as Z plus B over A divided by C over AZ plus D over A. So really, this is the same as studying matrices of the form 1, B over A, C over A, D over A. So this is a really good technique in mathematics. Without loss of generality, we can often renormalize, we can rescale so that something equals 1, unless it equals 0. We can't rescale something to be 1 if it was 0. So we have two cases, either it's 0 or I adjust it to being 1. Okay? And now you can probably play some games maybe with the denominator as well if some things are not 0. And when we go to this case over here, what can you assume is going to be true about B? Or either B is not 0 or B is B.
Either B is 0 or not 0.
B equals 0 or B equals, be more specific, which non-zero?
Specific.
We should be able to adjust things so without loss of generality, either B equals 0 or B equals 1. And so you can probably do your analysis like this and then inflate things. So the idea is to try to make these calculations as doable as possible. Okay. So the next is proposition 6.19. It has 3 parts to it. So the first 2 parts is let's let G be a group and let G act on some set X. So if I choose a little x, then the stabilizer is a subgroup of G. Seems reasonable. G sub X is going to be a subset of G. For us, for things to be interesting, we really like things to be subgroups. I'm sorry, did I say subset? If I said subset, I meant to say subgroup. The stabilizer is a subgroup. The next is we're going to define an equivalence relation. We're going to say X is related to Y if Y equals G times X for some G. And then we're going to show that this is an equivalence relation. So an equivalence relation has 3 properties. It's reflexive, it's symmetric, it's transitive. And so there's a nice correspondence between the equivalence class of X and the orbit of X. All right, so let's prove. So to prove it's a subgroup, what do we have to show? What do we have to do to show something is a subgroup? Closed. What else? Identity. What else? Inverses. And which is the easiest? Associativity. Why? It's inherited, right? Okay, so associativity is easy. What about the identity? Is the identity element in the stabilizer of X? Yeah, by the definition. When we were defining what does it mean to have a group action, one of the things we said is the identity has to send X to X. So the identity is going to be in it. What about inverses? Well, if X equals, I'm sorry, if Y equals G of X, then X equals G inverse of Y. Oh, I'm sorry. I'm sorry. I'm doing the next part of the problem. I'm sorry. We want to show if G is in the stabilizer, so is G inverse. But if G of X equals X, what does that imply? Multiply by the inverse. And so we get X equals G inverse of X. So G inverse is in the stabilizer. And I'll leave closure as an exercise. So the stabilizer is going to be a subgroup. The next thing we have to do is we have to show it's an equivalence. And so there's 3 properties for an equivalence. So the first is reflexive. Is X related to X? Is there some G such that X is equal to G times X? Yes, what should we take? Yep, take identity. Yes, just take G equals Z. So the next is symmetric. if x is related to y, that means y equals g times x for some g, thus x equals g inverse of y, and we now get y is related to x. And then I will leave transitive as an exercise. Show if x is related to y and y is related to z, then x is related to z. It's just a straightforward, just chasing everything. Okay, so now this is where things get interesting. There's a well-defined bijection where we look at g mod g sub x, the stabilizer. So this is the stabilizer here. And this is the orbit over here. And a bijection means that there's a one-to-one onto map between these two. So in particular, they have the same size. And it's defined as the following. Take any coset of the stabilizer, choose any element of the coset, and then the output is just that element g times x. So in order for this to be well defined, it shouldn't matter which element in the coset we take. Now remember, in the last class, we actually saw that it might make a difference when we were trying to multiply cosets. Do we take this element, do we take that element? Depending on which representatives we take, we saw that the answers could be different. So it's really nice here that no matter which element you take in the coset, it's going to have the same effect. Let's assume G1 and G2 are both in the same coset. And if they're in the same coset, that coset has to be of the form some G times the stabilizer. Okay. What does it mean for G1 and G2 to be in the same coset? Well, it means there exists, let's call it maybe G1 tilde, G2 tilde, such that G1 equals equals G times G1 tilde, and G2 is G times G2 tilde. Because if they're in the same coset, then they've got to be of the form G times something in that coset. It doesn't have to be the same thing, and that's why I'm going to do a different subscript for each. Now let's try to show that G1 and G2 have the same impact on X. So, and here, G1 and G2 tilde are in the stabilizer. So what would G1 of X be? That would be G1 tilde of X. But what's G1 tilde of X? Because G1 tilde is in the stabilizer of X, what is G1 tilde of X? So what is the stabilizer? The stabilizer is all the things that leave little x alone. And if I tell you G1 tilde is in the stabilizer, then when I apply it to x, what do I get? I get x. So this is just G times x. Similarly, if I look at G2x, that's the same as G2 tilde of x. What is G2 tilde of x going to be? Also x. So it's the same. So what we see is that if I take two elements in the same coset, they will have the same impact on x. And the reason is if they're in the same coset, they differ by multiplication on the right of some element in the stabilizer. And since the stabilizer leaves little x alone, they're going to have the same impact. And so now this is showing us that we do have a well-defined map. So we need to show that this map is one-to-one. We need to show that this map is onto. So imagine we have, so the first thing is it clear that this map is onto? So we can write G as a union of, let's call it GK times the stabilizers. And so when we look at what happens when we apply big G to X, we get the orbit. So big G on X is the orbit. That's going to be the union of GK stabilizer acting on X. But what's the stabilizer acting on X? So we take the stabilizer of X and we act on X. What do we get back? X. So this is going to just be the union of GKX. So the orbit really is going to be the same as this. All we have to do now is make sure that we don't have two different cosets going to the same element in the orbit. We've clearly shown that we get everything in the orbit. Everything in the orbit has been hit from one of these cosets. We just have to make sure that two different cosets don't go to the same thing. So assume, say, GKX equals GLX. What does that imply? So we're assuming two different cosets get mapped to the same element in the orbit. I'm sorry? Not necessarily. Because remember, they don't have to be equal. They could differ by an element of the stabilizer. So if we know GKX equals GLX, what could we do to both sides? We're trying to get the stabilizer. The stabilizer is all G's that fix in X. So we want to isolate an X. How could you isolate an X from this? Yeah, multiply by GK inverse. And then we get X equals GK inverse GL of X. So this must be in the stabilizer of X. So again, we're trying to use the information we know. We know something about the stabilizer of X, so I want to try to isolate X because then whatever is hitting it has to be in the stabilizer. So we know GK inverse GL is in the stabilizer. So that means GK inverse GL is equal to, let's call it some G in the stabilizer of X. Or GL equals GK times G. So the coset GL of G stabilizer is the same as GK G stabilizer, but that's just GK times GX. Because little g is in the stabilizer of X, when little g hits G sub X, you just get back G sub X. So this shows you that the only way two cosets could have the same output is if they're the same coset. So we just said, assume two cosets are mapped to the same element of the orbit. Well, then that means GK inverse GL is in the stabilizer, and then that means that the two cosets are actually the same. So we do have an equivalence between the two. And so in particular, because of this equivalence, we now know the cardinality of the number of elements in the orbit is the cardinality of G divided by the cardinality of the stabilizer. So this should hopefully remind you of a theorem about sizes of groups that we did earlier. So whose theorem was this? Lagrange. So Lagrange told us the cardinality of G is the cardinality of the cosets G mod H times the cardinality of H if H is a subgroup. So for us, we now have a group G. Our subgroup is going to be the stabilizer. And we just showed the number of the size of G mod Gx, the stabilizer, is equal to the size of the orbit. So we can substitute this into Lagrange's theorem. So by Lagrange, we get the size of G equals the size of G mod G sub x times the size of G sub x. Or the size of G mod G sub x is equal to the size of G divided by the size of the stabilizer. But this is just the size of the orbit. So that's the orbit. That's the size of the group divided by the size of the stabilizer. So this is an extremely valuable result. And it relates the size of the orbit to the size of the stabilizer. So once we know how many elements are in the group, if you tell me the size of the orbit, I know the size of the stabilizer. If you tell me the size of the stabilizer, I know the size of the orbit. And we're going to see a lot of wonderful consequences of this result. Okay, so the first big consequence is essentially immediate. So it's the orbit stabilizer counting theorem. So G is going to be a finite group. It's going to act on a finite set X. And then what it says is choose X1 through Xk in X so that G acting on X1 all the way up to G acting on Xk are the distinct orbits of X. Which makes sense. I mean, every element has some orbit. If two elements are in the same orbit, just collect them together. I only need one representative. And so we'll call those representatives X1 through Xk. And then what this is saying is the size of X is just going to be the size of the number of orbits. Because no element is going to be in two different orbits. Remember, G has inverses, so if you have one element in two different orbits, you can actually get anywhere. And now what we're doing is we're just using the thing we proved a moment ago. So just one moment ago, we showed that the size of the orbit of X is equal to the size of G divided by the size of the stabilizer of X. And now we just sum over the orbit representatives. And we get this formula. So it's basically just applying the result we had, a moment ago for each representative orbit. So any questions about this result? It's amazing how many things we can get from this. Especially if we choose G to have a very nice structure. So if I tell you G has 12 elements, what can you tell me about the possible subgroups if it has 12 elements? What do you know? You got to say it in that order? Because you want to do it methodically so you don't miss anything. Because you actually missed something. 1 and 12. So normally you go 1, 2, 3, 4, 6, 12, or 12, 6, 4, 3, 2, 1. The possible subgroups, their orders have to divide the order of G. So we're frequently going to look at G is going to have a prime power number of elements, or something close to a prime power number of elements, which means there won't be that many possibilities for the order of the stabilizer, because the stabilizer is going to be a subgroup. Okay, so the next thing is let G be a group. The center of G, I can't remember if we've talked about this before, denoted by Z of G, is the set of elements of G that commute with every element of G. And so what that means is you give me any element G prime. If G is in the center, then G prime equals G prime G. So it turns out that the center is a subgroup. And in fact, not only is it a subgroup, it's a normal subgroup. And if you think back to what we were talking about in the last class, when we were trying to figure out when is coset multiplication well defined, we said, well, if the group is abelian, everything is okay. And then we did make some comment if the subgroup we took was actually the center, the set of elements that commute, then everything would be okay. So what I'll do is I'll quickly sketch the proof that it is a subgroup, and I'll leave it to you to prove that it's a normal subgroup. So what do we have to do to show that it's a subgroup? It's the same as always. We have closure, we have inverse, we have associative, and we have identity. Is the identity in the center? Does the identity commute with everything? Yes, that's no problem. What about associativity? It's inherited, right? And then for the inverses, if for all G prime, we have G prime equals G prime G, we want to somehow get something involving G inverse. What can we do? How can we get G primes? How can we get G inverses from this relation? So we have G prime equals G prime G for all G prime. We want to show that we can replace G with G inverse. Yes. G prime is just, you're in the center. G is in the center. If for any G prime, G prime, it's a generic element. So we know for every G prime, we have G prime equals G prime G. We want to show that if we take any G prime, this works using G inverse rather than G if G is in the center. So we start with G prime equals G prime G. How could we get G inverse from this? Okay, on the left or on the right or both? Left, right, or both? Both. So we know G inverse G prime G inverse equals G inverse G prime G inverse. Well, this is just going to be G prime G inverse equals G inverse G prime. So G inverse is in the center. So the proof is actually pretty straightforward. Just once I have the relationship for G, I just have to somehow manipulate it to get a similar relationship for G prime. I'll leave closure to you as an exercise. Okay. So now let's let P be a prime and let G be a finite group with P to the n elements for some n greater than or equal to 1. Then the center is more than just the identity element. So there's something other than the identity element in the center. Why do you think I want to assume that n is greater than or equal to 1 when I have G's of the form P to the n? Well, n has to be a non-negative integer. What's the only other non-negative integer? 0. And if I take n equals 0, then G would be a finite group with one element. What's the only finite group with? It's got to be the identity. So there's no chance that this result could be true if n equals 0. So we want n to be greater than or equal to 1. So this is a nice result that G has a non-trivial center. Now there's a lot of possible actions that G can have. And it depends on what set it's looking at. What theorem do you think we're probably going to want to use to prove this? What theorem do you think might be useful to prove this? Yeah, we just proved this orbit stabilizer counting theorem. So maybe we can somehow apply this. If we're going to apply this, we have to figure out what should we choose for the group action and what should we choose for the set X. If you don't like someone, there is a profane thing you could say that they can go do to themselves. When you're looking at G as to where could G act, what's a very natural place for G to act? Give me a set that G can act on. Itself, right? You can go tell G to go act on itself. Now the question is, can we find a way to have G act on itself that's consistent with the two desired properties? The identity has to leave things alone and it has to be associative. So there are two really good ways to have G act on itself. We could define G dot X to be Gx, and we can define G dot X to be G inverse XG. And this is called conjugation. So these are both great ways to have G act on itself. And so what we're going to do now is we are going to prove that the center is non-trivial, that it has more than just the identity element. So we're going to choose X to be G, and we have to decide how do we want to have things act. So let's try G dot X is going to be G inverse XG. So what does it mean if you're in the stabilizer of X? So if G is in the stabilizer of X, then G inverse XG equals X, or what does that mean? So how might you rewrite G inverse XG equals X?
XG equals G.
Yeah, XG equals GX. So if you're in the stabilizer, you actually commute with X. Okay, so we know, uh-oh. Still recording. We seem to have lost the screen share. Okay, good. Got it back. All right. So now we know that, let's say the cardinality of X is going to be some orbits. We can write X as, union of, say, some orbits, G, X, K, and then that's going to be the same as the union. I'll do it like that. And then using the orbit stabilizer theorem, the size of X is going to be the sum of the size of the orbits, which is going to be the sum of the sizes of G divided by the sizes of the stabilizers. What do we know about the size of X? For this problem, what's true about the size of X? It's equal to the size of G, which is equal to what? Which is P to the N. So we get P to the N is equal to the sum of P to the N divided by the size of the stabilizer of XK. The left-hand side is a multiple of P. Now, if I look at the right-hand side, one possible orbit is the orbit of the identity. How many elements will be in the orbit of the identity? 1. So we know that, if we look at the sum of the orbits, it's equal to 1 plus stuff, where this one is coming from the identity. But when you look at the cardinality of the stabilizers, what can you tell me about the size of the cardinality of the stabilizers? Right, so G has p to the n elements. The stabilizer is a subgroup of G. Nope. Can't say it's less than p to the n. Yeah. What can you tell me about the cardinality of the stabilizer? It should divide p to the n. So there's two possibilities. It is either p to the n or it's not. Is equal to 1 times the number of k such that the size of the stabilizer equals p to the n, right? Because in that case, p to the n divided by that is just going to be 1. Plus a multiple of p, as the stabilizer has order less than p to the n, so p to the n divided by p to the l is a multiple of p as L is less than n. So if you think about what's going on, we know there's at least one element whose orbit has just one element. And if the stabilizer is all of p to the n, then that's going to give us a 1. And if the stabilizer is less than p to the n, it's going to give us a multiple of p. So because the left-hand side is a multiple of p, and this is a multiple of p, what can you tell me about this? Multiple of p. And if the order of your stabilizer equals p to the n, then you're stabilized by everything. So you're in the center. So in fact, we've proved more than the center has at least 2 elements. What did we prove? The center has at least how many elements? So this is a multiple of p. This is a multiple of p. Has to be multiple of p, right? There have to be at least p elements in the center. This, of course, also makes sense because the center is a subgroup, and the only possibilities for its order are powers of p. Does the proof make sense?
Why can't we cancel p to the n? And then it would be 1 equals.
Well, we could. There'd be one would be a sum of fractions,
Yeah,
but that wouldn't be as useful.
yeah, but we know that the sum 1 should be equal to sum of fractions, right?
Right.
And we know that g for the identity equals 1, which means that one of the elements in the sum equals 1. In the right.
Okay, so let's see.
Doesn't mean that the other elements must not exist.
So if we take the identity element, no, because if we take the identity element, you wouldn't get 1, you would get 1 over p to the n. You'd get 1 over p to the n.
Okay.
Yep. And so you can, of course, and when I was giving the lecture, I actually thought for a moment, well, we could just cancel the size of the g's, but that's not going to help us. It's really useful to keep it like this so we can keep track of which things are multiples of p. And so there have to be a good number of elements whose stabilizer is everything, because otherwise we would not have the multiple of p. Okay. Why do we care about stuff like this? It turns out as a really nice corollary, and I'll just leave this for you to see in the book. If you have a group of order p squared, then the group has to be abelian. So we have a complete understanding. Well, okay, with a little bit of work, we'll have a complete understanding of all groups of size p squared. But we at least know that there can't be a non-abelian group of size p squared. So if G has p squared elements, then what are the possible subgroup orders? What could the subgroup orders be? 1, p, and p squared. So if there exists an x in G such that the order of x equals p squared, what does that tell you about G? So if I have an element that has order p squared, what must be true about G? So you've got an element of order p squared, and G has p squared elements. Yeah, it has to generate the whole group. Then G has to be generated by X. So G would be 0, X, 2X. We like to write things additively. We're doing p squared minus 1 times X. So if I have an element of order p squared, we're done. It has to be this. So now the next possibility is no elements of order p squared. Something like this. The set of all things, let's say x, y, is 0 less than equal to x, y, strictly less than c. It has p squared elements, all have order 1 or 2. So as a nice exercise, here is another possibility. Is there anything else? Is this list exhaustive? Can you find anything other than these? And we actually know enough now so that you can prove that I believe anything is isomorphic to this. And so I'll leave that as a problem to think about. Okay, so before we get to the last part of today's lecture, I need an identity. And somehow it slides things around sometimes when it moves from my computer to the iPad. So let's let P be a prime, n greater than or equal to 0, and choose some number m greater than 1, which is relatively prime to P. Then the binomial coefficient P to the n m, choose P to the n, is not divisible by P. And again, let's recall that if I give you n choose k, that's n factorial over k factorial, n minus k factorial, or you can write it as n minus 1 dot dot dot, n minus k plus 1 over k minus 1 dot 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 down to 1. So we claim that this binomial coefficient is not divisible by P. So another way of saying this is every time P occurs in the numerator, we have exactly the same number of powers of P occurring in the denominator. So we're going to break things up term by term. So we'll look at the first term, P to the n times m over P to the m. Then we'll look at P to the n m minus 1 over P to the n minus 1. And then P to the n m minus 2 over P to the n minus 2, and so on and so on and so on. When you look at the first, P to the n m, is it clear that we have the same number of powers of P in the numerator and the denominator? Yeah, we just have n copies. What about the next one? P to the n m minus 1 and P to the n minus 1. Yeah, how many powers of P? 0. So 0 until we get to P to the n m minus P. I didn't hear that. P to the n minus P. How many powers do we have for p in the numerator? So how many powers of p do we have in the numerator? So you're saying
Oh,
one. I have one power. I have one power. Yes. So I can factor out a p, and it's p times p to the n minus 1 m minus 1 over p to the p times p to the n minus 1 minus 1. The p's cancel. And we see that now we have, again, two numbers that have nothing in common. Let's see if for once I can actually copy something. No, but let me highlight it, but then let me paste. All right, never mind. Someday it'll work. So now instead of having p to the n m minus p, maybe I have minus p to the l. And the argument is extremely similar. I now just pull out a p to the l, and I'll have p to the n minus l m minus 1 over p to the n minus l m. I'm sorry, no m there. Just minus 1. And we see again, the p to the l's cancel. So when I look at these fractions term by term by term, whatever number of copies of p I have in the numerator, I have in the denominator, they always cancel. So this number is going to be relatively prime to p. It's not going to be divisible by p. Okay? I need this as a key ingredient for the first Sylow theorem. So this is the last thing for today. Let G be a finite group, let P be a prime, and let P to the n be the largest power of P that divides the size of G. Then G has a subgroup of order P to the n. This is, to some extent, the kind of result we'd like to have. If I give you a group of size m, the hope is that any factor of m, there will be a subgroup of that order. So if I have a group of size 12, there will always be a subgroup of size 6. There will always be a subgroup of size 4. That's not always true. But in the special case, when P is a prime, and you take the highest power of that prime that divides G, then it will have a subgroup of size P to the n. So we at least have some information about the structure. Okay. So when we're going to prove this, what do you think we're going to use? What theorem? Yeah, the orbit stabilizer, whatever counting, I know there's 4 words in the name, right? That's, the big thing we were proving today. So this is probably going to be another consequence of the orbit stabilizer counting theorem. To use the orbit stabilizer counting theorem, you need several things. You need a group. We've got a group. You need a set that it's acting on. And you need a group action. Okay. So let's go and let's let X equal all subsets of G of size P to the n. I'm trying to prove that G has a subgroup of size P to the n. Let's consider all the subsets of size P to the n. And eventually I'm going to show that one of these subsets has a special property and is actually a subgroup. And then we win. So we're going to consider all the subsets of size P to the n. So what is the cardinality of X? How many ways can we take a subset of size P to the n of G? Well, it depends on what the order of G is, right? So we're going to proceed by induction. So we'll assume that the order of G is P to the n times m. So the base case, m equals 1. Can you prove when the order of G equals P to the N, that G has a subgroup of size P to the N? Yes, what's the subgroup? Yes, we win, G is the desired subgroup. So now we do the inductive step. So assume true for all m prime less than m, do for m. So now the size of G is P to the N m. What would be the size of X? How many ways are there to take a subset of size P to the N from a group with P to the N times m elements? Yes, so it's the binomial coefficient. It's P to the N times m, choose P to the N. Yeah, that might have been why a moment ago before we started the proof, we were actually looking at this quantity, right? I know that this quantity is about to emerge, so we studied it. What do we know about this? Not divisible by P. Okay, so we know it's not divisible by P. So now we can start decomposing things. So we know we can write X as a union of orbits, G say xk. And so if we want to look at the size of X, that's going to be the sum of the size of the orbits. And that's going to be the sum of the order of G divided by the order of the stabilizer of xk. So here, this is the orbit, and here, this is the stabilizer. What are the possible values for the size of the stabilizer? So remember, the size of G is P to the N times M. So we can say that the order of a stabilizer is going to be of the form, P to the L times, say, M tilde, where M tilde is relatively prime to P. Right? By Lagrange's theorem, it's a subgroup of G, so its order has to divide the order of G. So it's got to be P to some power. And in fact, we even know something more about M tilde. What do we know about M tilde? It's a factor of M. We don't really need to use that, but we have it. These are the only possibilities. So we know the left-hand side, this is not a multiple of P. But when I look at the right-hand side, every time I have a stabilizer, if the power is less than N, what do we know about it? If L is less than N, what do we know about that ratio? It's divisible by P. So we can split this up into two parts. Stabilizers L equals N. Stabilizers L is strictly less than N. And for these, the cardinality of G divided by Gx is a multiple of P. Right? So this whole thing here is a multiple of P. When sum over all of these. Because each one of them is a multiple of P. So if I look at all of the xk's whose L is strictly less than N, that's going to give me a contribution that's a multiple of P. The left-hand side is not a multiple of P. So what do we know about the number of stabilizers where L equals N?
It's not a multiple.
We know it's not a multiple of P, good. In particular, we know it's not. We know it's not zero. So cannot be empty, or the left-hand side is a multiple of P and right-hand side is not. So at least one orbit has a stabilizer with L equals N. There might be two, there might be three, there might be four, but there's at least one. So we know that, the order of that G sub X is P to the L times M tilde. If M tilde is less than M, we're done by induction, as this is a smaller group than G. So we know there has to be at least one orbit, at least one X, so that its stabilizer has the same number of P's as the full group. If the corresponding M tilde is equal to M, we could be in trouble. As long as M tilde is less, then we have a smaller group, and by induction, we're done. So the only thing that's left is what happens if M tilde equals M. So the size of the stabilizer is equal to all of G. Hopefully something bad is going to happen. So this means we have some set A with P to the N elements, and for all G in G, the claim is GA equals A. What does it mean if it's stabilizing? So we've got to be getting back our set. So do you think that GA could equal A? Remember, M is greater than or equal to 2, so A is a subset that does not equal all of G. But because G stabilizes, whenever we apply, it's going to return A to itself. How many elements are there in G? Yeah. So my claim is that if I want G of A to equal A, where does G have to live? If GA equals A, then G must live in where? So I have a subgroup, I have a subset of G. Where do we think G has to live? We're saying it's, think back to when you have subgroups. So imagine you have a subgroup. If you have an element acting on your subgroup, and you get back your subgroup, where does that element have to live? In the subgroup. So we have to think, what kind of action do we want to do? Maybe define, g dot x to be, g times x. Just do, left multiplication. And so now we know, for all g in g, GA equals A. Imagine we could prove that this implied that G had to be in A itself. If we knew that this implied that little g had to be in A, remember, G is in big G, which has p to the n times m elements. A only has p to the n elements. So that would be a contradiction. And then that would prove that, we can't have this case. So do we see that it's enough to show that if this is true, then the only way this can be true is if little g lives in A. If we could show that g of A equals A forces g to be in A, there's too many elements for this to hold. A only has p to the n elements, G has p to the n times m elements, where m is at least 2. Contradiction. We don't know that A has an identity element. We just know that there's some set with p to the n elements. But we do know we have group structures. Now, so assume GA equals A, for all G and G. Then what would GA inverse acting on A be? What would that equal? That would also have to be A, because we're assuming that GA equals A for any choice of element in G. Is GA inverse in G? Yes. So this is true as GA inverse is in G. If you want, on the previous line, instead of using G, I could use maybe G tilde. And so this is set G tilde equal GA inverse. So we have GA inverse A equals A. In particular, can you give me an element in A that might be really, really good to have GA inverse act on? A. So GA inverse acting on A has to be an A. But GA inverse A equals G, so little g is an A for all G and G. And we just showed that there are too many elements. A only has, the cardinality of A is p to the n. The cardinality of G is p to the n m, which is greater than p to the n as m is greater than or equal to 2. Contradiction. So we got a contradiction in that case.
Yeah, but I just do not understand the connection between the first two sentences.
So we know that there's some element whose stabilizer is all of G. And our set, the set X that we're looking at is the set of all sets of size p to the n.
Yeah.
So we have some set A with p to the n elements, such that whenever we act on it by an element in G, we get back A.
Yeah, but
Well, if you, from the previous page, we saw that there had to be at least one stabilizer who has p to the nth power.
yes.
If everything had a p to a smaller power than n, then we would have a multiple of p on the right-hand side. We don't have a multiple p on the left-hand side. So there's got to be at least one element who has a stabilizer of the form p to the n times m tilde.
Yes.
The problem is, if that m tilde is m,
Yeah.
we might not have our problem solved. Remember, we're trying to show that there is a subgroup of size p to the n, and we're proceeding by induction. So if we have m tilde is less than m, this is a group that now has fewer elements and we're done. So the only case when we're not done is if m tilde happens to equal m, and we have a stabilizer now that has exactly the same number of elements as the original group. In fact, it is the original group. And so we just have to show that that case can't happen.
And because we suppose that m tilde equals m.
Well, there's two possibilities. If m tilde is less than m, we're done by induction.
Yes.
If m tilde equals m, we're not done. So we just have to show that that case can't happen.
Yeah, I just don't understand how we're not done if we've proved by contradiction that if m tilde equals m, then m tilde equals m.
No, we're showing the case m tilde equals m can't happen, that it leads to a contradiction.
No, I got the whole previous thing.
Right.
I just do not understand how exactly, because we suppose that there exists A such that it has p to the n elements.
No, well, everything has p to the n elements. X is the set of all subsets of size p to the n.
A is the set.
A is one of the elements of X.
Yes.
So
We
A is an element of X. And it's an element whose stabilizer is all of G. That's the case we can't handle. As long as the stabilizer is not all of G, we're done by induction. And so now the possibility is, well, what if there is some element X? And so that element X, what does it mean to be an element X? Well, it means it has to be a subset of size p to the n.
Okay, I got it.
So now we have a set of size p to the n. Let's try to get some problems. Well, if we actually have the stabilizer as everything, that's too many elements, because then we can show that everything in G is actually in A, but there's not enough spaces in A. A only has p to the n slots, and you're trying to get m times p to the n objects.
Yeah. Okay, got it.
Yep. And that finishes, and this is a well-deserved QED box. We'll even write QED. Yeah. This is a major result. So we've just shown that no matter what group you have, if you take the largest power of the prime that divides it, then there will be a subgroup of that order. So unfortunately, if I give you a group of size 72, there has to be a subgroup of size, come on, 9, and there has to be a subgroup of size 8. But we don't know if there has to be a subgroup of size 6. We have no knowledge of something like that. We have no idea if there has to be a subgroup of size 4. Okay. All right, so this is definitely a good place to stop. This finishes what we're going to do of chapter 6, and then I think we're going to be moving on to chapter 8 next.